So method of section. Method of sections, if the forces in only a few members of a truss are to be found, so you want to know the specific forces at the specific members. So the method of sections generally provide the most direct means of obtaining these forces. So you don't have to analyze each joint, but rather you analyze a section of joint so that you can target which member that you want to analyze. So this method consists of passing an imaginary section. You cut an imaginary line through the truss and thus cutting into two parts. So provided the entire truss is in equilibrium, so the condition is that the truss is in equilibrium, so each of the two parts must also be in equilibrium. So that's the law that we are following. So if it is in equilibrium, summation fx, fy moments equal to 0, so the two parts should be in equilibrium. So these three equations, fx, fy, and a moment of equilibrium may be applied to either one of these two parts. So you cut into two sections, so you can apply the three equations into either parts, and then determine the forces at the members of the cut section. So a decision must be made as to how to cut the truss. So you need to determine where to cut. Specifically, if you want to find specific members, so you cut at that members. So in general, the section should pass through not more. This is the rules. If you don't follow these rules, so you can't solve your equation. So not more than three members. So there's four members there, so you need to line your cut. If the force in GC is to be determined, section AA will be appropriate. That's why let's look at this. So let's say you want to find GC here. So you want to cut at AA. You cut at AA. So when you cut at AA, so you can do a method of section at these two parts. So you have the first part here and the second part here. This is the second part. So this is the second part and this is the first part. So you can apply the equation on each part so that you can determine the value of GC, the force acting in members GC. So also the member forces acting on one part of the truss are equal but opposite. So this is similar to method of joint where you have a member here and then member here and then you cut here. So the force, if the force is acting to the right away from the joint, so uh, the other half would be in the opposite. So they would cancel out each other. So the three unknown member forces, this example, FBC here, so FBC here, FBC, FGC, and FGF can be obtained by applying the three equilibrium equations. So we apply the equations on either part, so you can solve for this and this. So when applying the equilibrium equations, consider ways of writing the equations. So you should pay attention to how you write the equations to yield a direct solution for each of the unknowns rather than to solve the simultaneous equation. So you write the equation to have a direct solution of each unknown. So this to practice. You practice more so you can get the how the equations are solved, so you can solve the equation faster, and you can write up the equation that helps you analyze the equation and the forces. So let's take a look at this example 3.5. Determine the force in members GJ and CO of the roof truss shown in the photo. And dimensions and loadings are shown. State whether the members are in tension or compression. So you need to know the value, and then you need to know the state, whether it is tension or compression, and reactions and supports have been calculated, so it's been calculated for you. So it'll be faster. So you have your AY here, IY here, and then your AX is equal to 0. So you want to find GJ and CO. So this is your GJ and CO. So the book advice for you to cut at B and cut at A. So as you can see here, the number of unknown. Let's take a look at number of unknown here. So when you cut at B, you have PO as unknown number 1, and then CO is unknown number 2, and then CD is unknown number 3. So it satisfies the equation because you only have 3 equations. So you have 3 unknowns, 3 equations, and then you can solve your unknowns. Similar to this, when you cut at AA, so you have one unknown here, JK, and then you have another unknown here at GJ, and then you have the third unknown is TH. So still you have um, you follow the rules and have the equivalent numbers of unknown and equilibrium equation. So it is important for you to really decide your where to cut, because if you let's say you cut that cause 4 numbers such as this, you have 1, 2, 3, 4, 5. You have 5 unknowns, and because you cannot solve the forces directly. You need more equation from other members, so it will be hassle. It will take too much time for your analysis. So decide where, because in final this method is required, because if you do joint method on the equation on the question that requires for you to do method of section, so you spend a lot of time on that question. Instead you should have spend less time if you use method of section. So be very fluent, be very competent in these two methods. So let's take a look at the solution. 3.5 solution. The free body diagram of member GJ can be obtained by considering section AA. So direct solution for FGJ can be obtained by applying moment at I. So you're taking moment here. So by applying principle of transmissibility, FGJ is slided to point G for simplicity. With anti-clockwise moment as positive, a summation of moment I is equal to 0. So you transmit the force of GJ to point G. You point the point GJ to point G. So instead of you resolve the forces of GJ here, you resolve to here. So your moment arm will be 2. So in this section is a bit complicated. You can do either one. You solve the using sine theta. So your FGJ is here, sine theta. So this is your FGJ after you resolve into a y component. So your moment arm is 2 meter. So that's why your 2 meters. So sin theta is here. This is your theta. So this is your opposite, and this is your hypotenuse. So sin theta of FGJ is equal to this force, which is you resolve to here. This is trigo, and then you have 1200 times 1.5. So you solve for it. So very short. Instead, you don't have to solve for GH or KJ to get the value of GJ. So next is CO. CO we cut to B. So moments will be assumed about point A in order to eliminate FOP and FCD. So take that point A. FOP is cancelled out, no moment arm, and FCD is also don't have any moment arm. So with anti-clockwise is positive. So 1200 times moment arm of 1.155. Then your FCO is perpendicular to point A with moment arm of 2 meters. So your FGC is equal to 693 Newton, which is in tension. This is actually FCO. Typo here. Okay, another example, example 3.6, determine the force in members GF and GD of the truss shown. State whether the members are in tension or compression. Usually question will come like this. You need to know the value and you need to know the state of the members, tension or compression. And ratio at some point we calculated. This is rare. Usually in exam you need to calculate yourself, doing the free body diagram of a whole structure. So we want to know GF, GD, so GF and GD. So we cut at A, most logically, practically to cut at A. So your unknown will be GF, GD and CD. So the distance of EO can be determined by proportional triangles or realizing that member GF drops vertically 4.5 minus 3 meter in which is equal to 1.5 meter in 3 meter. Which is a proportional triangle. Hence, to drop 4.5 from G, the distance from C to O must be 9 meter. It is a proportionate. So we want to find the distance EO. Uh, we want to find the distance EO. So EOO is an imaginary line being created in this solution. For that, you can cancel out certain moment. For example, in this, you cancel out FCD and FTF, not mistaken. So you want to do proportional triangles here at point O. So GF, so here is GF. So this is a proportional triangle. So this is O. So G to the F drops by this value 4.5 minus 3 meters. So this value is 1.5 meter. So G to the F drop 1.5 meter in 3 meter. So a drop 4.5 from G to distance from C to O. From C to O, this distance. So the drop is proportionate. By 3 meter to 1.5 meter. So if it is 4.5 meter, you want to drop 4.5 meter. So your 3 meter must be 9 meter. And so if it's proportional, because when you want to drop 3 meter here, it is proportional to 1.5. So if you want to drop 4.5 meter here, 4.5 here, right? So how much is this value? What is the distance here? So that's what we want to find. So based on this proportional, and based on the proportional, you will see that this is a three times higher. So by proportion, you should also multiply this 3 by 3. So that's how you get 9 meter. So basically 9 meter from C to O, 9 meter. So that is your moment arm from C to O. So continue, and the angles have a GD and FGF. Make with the horizontal are inverse tangent of 4.5 divided by 3, and then the tangent of 4.5 divided by 9. So your FGD and FGF, FGD and FGF and FGD. So the angle, this is determined from this. So based on your equation, based on your figure here, this is a triangle. So you want to know angle here and then angle here. So how do you find that? Is based on this distance, uh, tan theta, tan is opposite divided by beside. So the opposite is 4.5, and then your adjacent member is adjacent triangle is 3 meter. So then this is theta, theta 1. And for theta 2, this is a triangle. So we know this 3 meter, and this we know 1.5. 1.5. So that's how you get 4.5 over 3. So this is the use 4.509, because 4.509 is taken up to this point. So the angle is similar. The angle is similar. So that's how you get tan inverse. Tan inverse. Tan inverse. Or the original equation is tan 2 lah. Tan 2 is equal to 4.5, which is here. 4.5 over 9. So that is basically trigo. You want to know the angle so that you can resolve the force into each axis. So the force in GF can be determined by directly applying the moment at D. So FGF is slided to point O with anti-clockwise moments. FGF here is slided to point O, taken at D. So this is FGF slided because it's in the same line. Parallel, one line, single line, moment, same moment. Uh, so this is your equation, -7 times 3 moment arms. So this is 7 taken at point D, so it will be clockwise, so negative. The moment arm is 3, then you have 2 times 6, uh, 2, 2, the moment is taken at O, sorry. So 7 taken at O, so this is clockwise. So clockwise is negative, right? So, and the moment arm is 3 meter. Then another one is this moment 2 kilonewton times this is the distance 6. So counterclockwise positive. So there you have it, positive, negative, moment arm 6, moment arm 3. And then you have FGD. FGD. So you single out FGD here because FGF is not here. Uh, FGF is not here, so FGD is single out here, so you can get FGD. So for FGF, we use moment at point D. FGF is your moment point D. So moment at point D, you will cancel out these forces. This also cancel out, and this GD is also cancel out. So you single out FGF only, right? Only FGF is taken into consideration because moment at D. FGF you can either resolve here, or you can also put it here with moment arm of 6. So here you have it, moment arm at 6. This is your resolve FGF to Y axis. And this 7 times 3 is this forces, external force, reaction force, times the moment arm of 3 at D. So using method of section is important to, is good to single out forces, and to target force in member, and also you need to be competent in uh, in 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 cancelling out the forces in terms of in the equilibrium of moment, like what we did in this two past example. So most of it using moment like this moment O, and this moment at D, uh, and also at this moment at A. So basically moment can cancel out, provided that the forces, that unknown forces is in line or concurrent towards the, or heading towards the point of moment. So you don't have any moment arm for that forces. So compound trusses are formed by connecting two or more simple trusses together, either by bars or joints. This we've talked about. We have three types of compound trusses. Three types, and it is best to analyze by applying both method of joints and method of section for compound trusses, because you have simple trusses combined together. So simple trusses can use method of joints, but for the bars you can use method of section. So by combining these two methods, you get a lot faster analysis, and less error, human error, calculation error. Let's take a look at this example. So example 3.8 indicate how to analyze the compound truss as shown. Reactions have been calculated. So you have these two groups of trusses, simple trusses connected by bars, these bars. So this book suggests to cut at A, to cut into two sections. So you will identify, you will determine the value of HG and JB, CB and CJ. So and the rest of the trusses you will use method of joints. So the force is in HG is determined as by taking moments at O, moments at O, moment at O. So taking moments at O, this is your equations for moment at O. You have uh, external forces, external forces of 5 kilonewton. This is the external forces. Actually there's a typo here. It is actually moment at C, moment at C actually, moment at C. So when you take moment at C, so you cancel out FJC and FBC. So you'll be left with FHG, which is 4 kilonewton and 5 kilonewton. That's why your 5 kilonewton is clockwise, because the center of moment is here, with a moment arm of 4 meter, moment arm 4 meter, and then your this 4 kilonewton external load, external force, with 2 meter moment arm, and then your FHG is with moment arm of force in 60 degree. Is due to this, when you resolve this 4 meter, you have this triangle, So you have this triangle of 4 meter. Uh, this is your triangle. So 4 meter here resolve to 60. So you get this value. You will get this value, the vertical value. You want to find the distance of angle, this triangle. So you want to know this distance. This is the distance that you want to know. So this is your angle 60. So you can use 2, you can use 4, you can use this is so this is 4 meter as shown here. This is 4 meter. It's similar. This is 4 meter. So we want to know here. So uh, sin 60 equal to here divided by 4. So 4 get over here, so you get unknown length b for sin 60. So this is trigo. I can solve it in many ways, but it takes time to solve for trigo. So that's how you solve for HG. And the joints of this truss can be analyzed in the following sequence. Then you continue when you found your HG, you can start going backwards. To join A, get AB and AI, and then join H, you get HI and HJ, and I, and then B, and lastly J. And then it's a mirror. A more direct method for analyzing a complex truss, referred to as a method of substitute members, will be shown in the example. So this is a more direct method, substitute members. So example 311, determine the force in each member of the complex truss as shown. Assume joints BFD are on the same horizontal line. So BFD is same plane, same line. State whether the members are in tension or compression, similar as before. So first is reduce the stable simple truss. Need to do reduction on the stable simple truss. So each joint has 3 unknown member performed by hand. So you have 3 each joint, and 1, 2, 3. So joint A also 3, and joint E also 3, and so on, except joint C. So external loading on simple truss. The support reactions on truss have been determined. You need to determine the reaction first before going deep into analysis of the truss. And then next you need to remove external loading from simple truss. The unit load acting on the truss is shown. These equal but opposite forces create no external reactions. So the unit load is applied on the truss at joint F and C. Then superposition, you do superposition. SdB is equal to SdB plus XSdB is equal to 0. So your superposition of dB is equal to imaginary dB plus XSdB, and by substitution negative 10 plus x times 1.167 equal to 0. So your x is equal to 8.567. So basically the original question is here. This is your original question. So all joints uh, three unknown members, unknown forces. 1, 2, 3. all the members. So what we want to do is we remove this member CF and substitute to BD. Which is still a truss that is stable and simple truss. As shown here, each joint has the unknown, so we reduce. Thus, the truss became like this. Once the truss became like this, you can determine force CB, CD, and so on. Because you have one joint having only two members, only two unknown forces. So you can calculate CB, CD, and then you join D and then join B. So as shown in the books, uh, so as I mentioned, the resulting truss is still stable and will not collapse. And then as shown in figure 3b, when you remove here, you remove the member CF and then you substitute to member BD. So the support ratio on truss have been determined. So using method of joints, we can first analyze joint C. To analyze joint C, you get CB and CD. And then joint F, you do joint F, where you see that FA and FE are zero force member. So FE and FA is 0. And then joint E to determine the forces of members EB and ED. So you find EB and ED. And then join D to determine forces in DA. Join D, determine forces in DA and DB. And finally join B. And finally join B, you will determine the forces in BA. Considering tension as positive and compression as negative, so these SI forces are recorded in column 2 of table 1. So based on this structure, all the substitution reduction, then you take away all the zero force member of FA and FE. So you get your value of each forces in each member as shown in this table. So in this column. So this is your calculation of each forces in members based on the force, external force of 5 kilonewton there. This was the actual force. So what you want to do next is remove the loading, remove the 5 kilonewton here. So you remove and then you put uh, unit load acting on the truss as in this figure. So this equals but opposite forces. So equal but opposite. So create no external reactions on truss. So the joint analysis follows the same sequence as discussed previously. So namely, you start with C, you find BD, CBCD, then you go to F, and this zero force member you exclude from the equation, and then E, D, and lastly B. So the result of SI forces, imaginary, you can say this is imaginary because we put unit load here, are recorded in column 3. So we record this column 3. So as a principle of superposition, so in the principle of superposition, the actual forces in the member is equal to force due to external load plus the force due to unit load should be 0 at point dB. Because why? Because dB, there is no member on dB in the actual structure. So that's how, because we want to find the value of x, what is the multiplier for for the forces, for the forces of unit load compared to actual external load. So this is only applied to dB. The as dB is equal to 0 is only applied to dB only. Only this member because it is an imaginary member. So substituting the value 2.5 here, the series in compression, and then this is 1.167 for unit load, the forces acting in members of dB due to unit load. So you get your value of x, which is 2.143. So the values of x are recorded in column 4. The value of x si, x times this value is given this column. So basically when you have this x value, so you can multiply it with all this si value, scb, scd, sfa, fe, sf, seb, and so on. So 2.143 times 0.77, you get 1.52, and 2.143 times negative 0.25, you get 0.536. So what you want to do is total up these two, so you get the actual forces acting in the members. It's a bit complicated, but it is a solution for solving complex truss. So this is your value. As you can see here, the value of SDB is 0 because it's a substitute member. Okay, so next video we will take a look on space truss.